All right, people, this is a vertical spring example problem. So please write down these, well, actually draw the diagram and first. So this is picture of a vertical spring. I have preset these values to what's on the slide. We're going to put a 90 kilogram mass at rest here, and it's going to bob up and down. Oh, I want you to see the velocity vector is what, oh, we want to turn damping to 0, sorry. We don't want the displacement. Okay. Oh, I guess I have to have that to show the natural length. All right, so wait here, let's do this. Here's where the spring wants to be, and then I won't turn that off. All right, so we're gonna put this at rest here. It is going to go bob up and down, up and down. You can see that the green, I'm turning this slow. The green line is the velocity, and you should note that it is a 0 at the turnaround and maximum when it passes equilibrium. 0 at the turnaround, maximum passing through equilibrium. Okay, so the green line is the velocity vector, also representing the kinetic energy squared. I mean, the velocity squared. The yellow vector is the net acceleration, right? The sum of the effect of the force of gravity and the spring. But I want you to notice that that is always pointing towards equilibrium. So when it's above equilibrium, gravity's winning and the net force is down. Boom. For an infinitesimal amount of time, 0, it's 0. And then the spring is winning and is pulling it back up. All right, so with no energy loss, this will oscillate forever and ever and ever. And if you looked at the position function, you would get a sinusoidal graph. So this is showing the motion. And then we have this ruler. Okay, so anyway, that is the problem. Let's turn that off. So draw whatever picture makes sense to you, and the spring constant is 26. The mass is 0.09. And we're going to do two questions, A and B. We're going to find the speed when passing through equilibrium. And then we're going to find the maximum stretch of the spring. Okay, so please write that down. And then I think it makes sense to do the problem here on this. Okay, so question number 1 is find, oh, will I be able to draw on this? I'm not clear. Let's see. No, because that's not my Cami document. All right, sorry. I'm gonna take a screenshot and I'll be back with you. All right, here we go. So given the spring constant, given the mass, find the maximum speed. Okay, again, this is a two-part problem. The first thing you have to do is find, oh shoot, and ignore that. That was part of the screenshot. Find the equilibrium point, and I believe this is the equilibrium point. Doesn't matter. We can pretend like it is. Equilibrium is about forces because it's when the forces are 0. So even if the question doesn't say draw a force diagram, which it probably won't because I'm trying to not prompt you through everything. So I want you to know, oh, this is about forces. You're going to draw a quick, easy force diagram and then say at that point, the forces are balanced. So K delta X minus mg is 0. Plug in what we know. And you get a delta X of 0.34 meters, which it doesn't look like when I was setting this up for a second period. It doesn't look like that, but that's where, if I set this up right, that's where the spring is supposed to be, not the midpoint of the mass. And I just made the ruler, I put the ruler where the mass, anyway, long story. Hopefully you trust me. That is 0.34 meters. So that's how much the spring is stretched. All right, so that's part 1 of this two-part problem. Okay, part 2 is find the actual speed at that point. So speed has to do with kinetic energy. Energy has to do with comparing 2 points. So the 2 points in space we know are point A, where we released it from rest. And I'm going to call this point C. I don't know that I'm always consistent about that. B would be where the bungee is unstretched. Oh, sorry. This is also where the bungee is unstretched. If you go back and remember, like, so in the bungee jump lab, you're going to drop the person from a height that is not unstretched. In this case, we are dropping the object from unstretched. And then again, my ruler was too low. So this is where we're dropping it from. Okay. So ignore this. I was thinking about the bungee jump lab. Sorry. Okay. So the rule is to set sea level to unstretched. What you want is your zero reference for UG and US to be the same spot. It makes your life easier. Okay, and we just calculated that equilibrium was 0.34 meters below that. So you are going to have to put the minus sign in yourself. When we solved for it 2 seconds ago, we got positive 0.34 because that's how much the spring was stretched. Oh, but since we were solving for delta, nope, never mind. You have to put the minus sign in yourself. Okay, hopefully that's not a problem. Okay, so now we're ready to say, oh shoot, we're going to need space. TME at A, I call this, equals TME at C. Because we want speed, which is energy, which means I'm carrying 2 points. Okay, this is where things get a little tricky. We decided that well, hang on. The 3 terms you could have are mgh plus spring stored energy plus kinetic energy equals mgh plus spring stored energy plus kinetic energy at C. All right. We're dropping the bungee jumper from unstretched. Like, don't have to, but that's what we did. It's not moving because we dropped it. We didn't throw it. What is tricky is we're also at sea level. Okay, your brain might want this to be, see, it's even labeled. You might want to call that sea level. We don't even know what that distance is. So what seems a little weird is that initially the system looks like it has 0 joules of energy. And you're like, well, that must be wrong. How am I going to get anything? How am I going to get spring stored energy? How am I going to get kinetic energy? I got nothing. I don't have any energy. But this is what happens. So I wanted you to see this in the example problem so you wouldn't freak out. All of those are 0. On this side, we're going to have mgh, which is 0.09 times 9.8 times h. I'm going to call this h. You can call it y, whatever. Plus, oh, sorry. We know that we are 0.34 meters below sea level. That's why I made a big deal about that minus sign. So what you're going to do is you are going to go below sea level so that you have enough energy to put in the spring and to be kinetic energy. Okay, so it's kind of like you're taking out your credit card so that you have other energy forms. Okay, and if you don't know what I'm saying, we just see that the math works out. So K is 2.6. Delta X is negative 0.34, but we're going to square it. Okay, that's why I like to set sea level to there. Then these two numbers are the same, nice and easy. And we are looking for the speed. Okay, so do not freak out if your total energy is 0. As long as you're going to continue to go lower than you start, it's going to be okay. All right, and then the numbers come out to be 0 equals negative 0.3 joules plus positive 0.15 stored in the spring, plus we don't know yet velocity squared. Okay, and then you get 0.15, bringing these over to the other side, equals 0.045 v squared, and then see everything's okay, it's going to work out. We're not going to take the square root of a negative number. You end up getting v is the square root of 0.15 over 0.045 which is the square root of 3.3 repeating, which is 1.83 meters per second. That is the speed at that instant. You could check your work by making this delta x a little bit more than like 0.3 or 0.39, a different number, since that's the maximum speed. Like, you could go through this whole exercise again and show that any other point you look, the speed is a little bit less, is something less than 1.83. But anyway, that is the problem. I hope that worked out for you. All right, then I'm going to clear everything out and we're going to do the second question. All right, so question B is find the maximum stretch, right? If you are running a bungee jump operation, you want to make sure the person turns around before they hit the water, I assume. Okay, so what you need to know at max stretch, that means that you're not heading down anymore, so it is a turnaround, so your speed is 0. So anything that's about speed, sorry, yeah, because its speed is 0. So again, this is like, even though it looks like it's about location, what's fundamentally true is, oh, it's a turnaround, my speed is 0. All right. If energy is conserved, it doesn't matter how you get, which 2 points you compare. So let's compare point A and E, our turnaround. So TME at A equals TME at E. You could also do equilibrium to E, but you know what? Let's make lives easy on ourselves. We already know that the energy at A is 0. Well, the energy anywhere is 0. But we've already kind of set that up. So you have no joules of energy. I erased it, but this is sea level. So at E, you could have mgh, you could have 1/2 kx squared, you could have kinetic energy. All right, but then, oh, max speed, that's a turnaround, V is 0. My mass was 0.09, this is 9.8. I'm going to leave this as h, that's what we're looking for, plus 1/2, 2.6. And again, the beauty of calling this sea level is this is h squared. And then you get let me see, you get 0 equals 0 plus 0.882h plus 1.3h squared. And then you get a quadratic where this is A, this is B, this is C. Plug that in your calculator, and you get a quadratic of 0 and negative 0.678 meters. All right, so in some of my old, I'm almost done, but hold on for a couple more minutes. In some of my old problem answers, I might have put the minus sign in here saying we know we're below sea level. To me, it makes more sense to just say I'm solving for h, and then this tells you that you want to choose the minus, the -1. Okay, and then check your work. The other turnaround point is kind of like, duh, we knew that. It was 0, because if we go back to the animation, oh, look, it's still going, right? That's a turnaround point, was at h equals 0. And what's confusing is where the mass is and where the spring is not the same spot. But h equals 0, h equals, let's see if the numbers make sense. About 0.7, right? So you can see h equals 0. Let's put the midpoint of the mass at 0 and 0.67. Hopefully that's oh man, 0.678. Anyway, those are your 2 turnaround points, and please record both answers. People are still only recording 1, some people, and I'm still taking off 1 point. Okay, the last thing I want to say is you can check your work. Add up the 2 turnaround points and average them, and you will get, it was, I think, 0.334. You will get the equilibrium point, because the position function we're going to see, oh, I can't write on this. The position function we are going to see at the end of the year is the mass is bobbing up and down in the spring, and it is sinusoidal. And so turnaround point, turnaround point, turnaround point, turnaround point, equilibrium. By properties of sine and cosine, this is the same distance above and below equilibrium. So if you average these two turnaround points, you are going to be able to check your work and confirm your equilibrium position. All right. So again, complicated, maybe not there's a lot going on, right? And so it is the same thing over and over again. So it is complex, but not novel. So keep practicing so that you know all the points, different position locations, like that. And thanks for listening.